Hello, everyone. In this section, we will introduce discrete BJT amplifier circuits, focusing on the common-emitter amplifier. So far, we have separately discussed the DC bias analysis of BJT amplifiers and the AC small signal analysis using equivalent circuits. A complete BJT voltage amplifier is built on a stable DC bias circuit. Then an AC input voltage signal is applied at the input, and an AC output voltage signal is taken from the output. The most common DC bias circuits for BJT amplifiers are shown here, the Case 3 and Case 4 circuits introduced in the previous sections. Besides those bias circuits, there is another DC BJT biasing method, as shown here. The base terminal is connected to the collector through the resistor RB. The current through RB is the current entering the base terminal, which is IB. The current leaving the emitter is IE, and the current entering the collector is IC. Therefore, the current through RC is IC plus IB, which is equal to IE. Therefore, from the collector side at VCC down to the grounded emitter terminal, the total voltage difference VCC is equal to the voltage drop across RC plus the voltage drop across RB plus the BE junction voltage VBE. Drop across RC is IE times RC, and the voltage drop across RB is IB times RB. Since IB equals IE divided by 1 plus beta, we can solve for IE. IE equals VCC minus VBE divided by the quantity RC plus RB over 1 plus beta. Here, RB over 1 plus beta comes from reflecting the base side resistance into the emitter current expression. Typical conditions, RC is much larger than RB over 1 plus beta. Therefore, IE can be approximated as VCC minus VBE divided by RC. Then IB equals IE over 1 plus beta, and IC is approximately equal to IE. In this way, the three terminal currents of the BJT are obtained. Next, we calculate the collector voltage VC. It is VCC minus IE times RC. Since the emitter voltage VE is grounded at 0 volts, the base voltage VB is approximately 0.7 volts, because VBE is approximately 0.7 volts according to the constant voltage drop model. After introducing the DC bias circuits of BJT voltage amplifiers, we now use the most common Case 4 DC bias circuit as an example to discuss the three discrete small signal voltage amplifier configurations. The first one is the discrete common-emitter amplifier shown here. The black components form the DC bias circuit, and the AC input and output are connected through coupling capacitors. A discrete circuit means that the electronic components are manufactured separately and then connected by external wires. Using coupling capacitors is a typical discrete circuit approach. In a discrete circuit, components can be removed or replaced. In contrast, an integrated circuit, or IC, means that all components are fabricated together and connected internally during fabrication, so the components are not detachable. Integrated circuits also usually avoid large coupling capacitors because they take up chip area. Returning to this circuit, the input signal is applied to the base terminal, and the output signal is taken from the collector terminal. Therefore, as discussed in the small signal analysis chapter, this is a common-emitter amplifier. As emphasized before, circuit analysis starts with the DC analysis. Only after finding the DC operating point can we determine the small signal model parameters of the transistor and then perform AC small signal analysis. During DC analysis, the signal frequency is 0, so the capacitor impedance, 1 over j omega c, is infinite. The coupling capacitors behave like open circuits. Therefore, the DC equivalent circuit becomes the circuit shown on the right, which is the Case 4 DC bias circuit discussed earlier. Notice that the AC signal does not affect the DC bias circuit. This is the purpose of the coupling capacitors. They block the AC signal from disturbing the DC bias. For AC small signal analysis, the impedance of a coupling capacitor, 1 over j omega c, approaches 0 if the capacitance is large enough. Therefore, in discrete amplifier design, coupling capacitors are usually chosen large so that they behave like short circuits for small signals and do not significantly attenuate the voltage signal. Also, DC voltage sources become short circuits to small signal ground. The AC small signal circuit is shown on the right. At the input node, where coupling capacitor C1 is connected, there are three branches, RB1, RB2, and the BJT base terminal. Thus, RB1 and RB2 are in parallel, and that parallel resistance is also in parallel with the input resistance looking into the BJT base. At the output node, RC and RL are also in parallel. At the emitter node, coupling capacitor C3 shorts the emitter to small signal ground, so RE is not seen in the AC small signal circuit. Therefore, we can simplify the circuit. The parallel combination of RB1 and RB2 is replaced by RB, and RC in parallel with RL is represented as an equivalent load at the output. The result is the simplified AC small signal circuit shown on the right. Because the BJT emitter is directly connected to small signal ground, it is convenient to use the pi model. After substituting the BJT small signal pi model, we obtain the equivalent circuit shown on the right. The resistor RO represents the contribution of the early effect between the collector and emitter terminals. In this circuit, RO is also in parallel with RC and RL. Therefore, if the early effect is included, the total resistance connected to the output node is the parallel combination of RC, RO, and RL. As in the previous small signal analysis, we begin by finding the input resistance Rin. The input resistance at the signal input node is Vin divided by In. From the equivalent circuit, the input current enters a node where RB is in parallel with the BJT base input resistance Rpi. Here, Rpi is the input resistance looking into the base terminal of the transistor. Therefore, Vin equals In times the parallel combination of RB and Rpi, and Rin equals RB in parallel with Rpi. The input voltage is then Vin equals Rin over Rin plus R sig multiplied by V sig. From the pi model, Vin is the same as Vpi in this circuit. Once Vpi is known, the output side controlled current is Gm times Vpi. Therefore, the output voltage Vo is negative Gm times Vpi, multiplied by the parallel combination of Ro, Rc, and Rl. The voltage gain of this CE amplifier is AV equals Vo over Vin, which is the same as Vo over Vpi, so AV equals negative Gm times Ro in parallel with Rc in parallel with RL. The open circuit voltage gain AVO is obtained when RL is infinite, so AVO equals negative Gm times Ro in parallel with Rc. If the early effect is ignored, Ro is treated as infinite. Next, the overall or global voltage gain is obtained. GV equals Vo over V sig, which equals Vin over V sig multiplied by Vo over Vin. Therefore, GV equals Rin over Rin plus R sig multiplied by AV. Substituting Rin equals Rb in parallel with Rpi gives GV equals negative Rb in parallel with Rpi, divided by the quantity Rb in parallel with Rpi plus R sig, multiplied by Gm times the parallel combination of Ro, Rc, and RL. Finally, we calculate the output resistance. Remember that the amplifier output resistance does not include the load resistance RL. We first set the input signal V sig to 0. Then, Vpi is 0, so the controlled output current Gm times Vpi is 0 amps and behaves like an open circuit. After applying a test voltage Vx at the output node, the test current Ix is Vx divided by Ro in parallel with Rc. Therefore, Rout equals Vx over Ix, which is Ro in parallel with Rc. This is the total resistance seen by the output test voltage. To summarize this CE voltage amplifier, the input resistance is Rb in parallel with Rpi. Usually, Rb is much larger than Rpi, so Rin approaches Rpi. As mentioned before, this input resistance is not high enough for an ideal voltage amplifier. The open circuit voltage gain AVO is negative Gm times Ro in parallel with Rc. The negative sign means that the input voltage signal and the output voltage signal have a 180-degree phase difference. Next, as discussed in the earlier small signal analysis chapter, one way to improve the limited input resistance of a CE voltage amplifier is to add a resistor at the emitter terminal. In a discrete circuit design, we would like to keep the DC bias circuit almost unchanged. Therefore, the total emitter resistance remains Re, but it is split into two series resistors: small signal Re and Re minus Re. The coupling capacitor C3 is connected between these two resistors. In DC analysis, the coupling capacitor has infinite impedance and behaves like an open circuit. Therefore, the DC bias circuit is exactly the same as the previous CE circuit, as shown on the right. However, in AC small signal analysis, the coupling capacitor is approximately a short circuit. In the AC circuit shown on the right, the emitter terminal now has the resistor Re connected in the small signal path. This Re increases the amplifier input resistance. Again, we replace the parallel combination of RB1 and RB2 at the input by RB. At the output, RC and RL are simplified as a parallel equivalent resistance. Then we substitute the BJT model into the circuit. This gives the equivalent circuit shown on the right. We again start by finding the input resistance Rin. As before, the input resistance is Rb in parallel with Rib. Here, Rib is the equivalent resistance looking into the base terminal of the BJT. Using the resistance reflection rule, the total emitter side resistance Re plus Re is reflected to the base side by multiplying it by 1 plus beta. Therefore, Rib equals 1 plus beta times the quantity Re plus Re. The same result can be obtained directly. Rib equals Vb, or Vin, divided by Ib. Since Ib equals IE over 1 plus beta, and IE equals Vn over Re plus Re, substituting gives Rib equals 1 plus beta times Re plus Re. This is why mastering the resistance reflection rule is useful for analyzing more complicated circuits quickly. After obtaining Rin, the input voltage is found by voltage division. Vin equals Rin over Rin plus R sig multiplied by V sig. Since Rin is Rb in parallel with Rib, this can also be written as Rb in parallel with Rib, divided by the quantity Rb in parallel with Rib plus R sig multiplied by V sig. Once Vn is known, the emitter current IE is Vn divided by Re plus Re. The output side controlled current is approximately alpha times IE. Therefore, the output voltage is Vo equals negative alpha times IE multiplied by Rc in parallel with RL. Substituting IE gives Vo equals negative alpha times Vn over Re plus Re multiplied by Rc in parallel with RL. From the expression for Vo, the voltage gain is AV equals Vo over Vn, which is negative alpha times Rc in parallel with RL, divided by Re plus Re. When RL is infinite, the open circuit voltage gain is AVO equals negative alpha times Rc over Re plus Re. The overall gain is GV equals Vn over V sig times Vo over Vn, so GV equals Rn over Rn plus R sig multiplied by AV. In terms of Rb and Rib, this becomes negative Rb in parallel with Rib, divided by the quantity Rb in parallel with Rib plus R sig, multiplied by alpha times Rc in parallel with RL over Re plus Re. Finally, we find the output resistance Rout. As usual, we first set the input signal source to 0. After V sig is set to 0, IE becomes 0, so the controlled current source is 0 and behaves like an open circuit. When a test voltage is applied at the output, the equivalent circuit shows that Ix equals Vx over Rc. Therefore, Rout equals Vx over Ix, which is Rc. The load resistance RL is not included in the calculation of Rout. Now we compare the discrete CE amplifier with and without the small signal emitter resistor Re. If Re equals 0, the input resistance is Rb in parallel with Rpi. Under typical conditions, Rb is much larger than Rpi, so Rin is approximately Rpi, which is 1 plus beta times Re. The open circuit voltage gain is negative Gm times Rc, or equivalently negative Rc over Re. When Re is inserted at the emitter in the small signal circuit, the input resistance becomes Rb in parallel with Rib. If Rb is much larger than Rib, then Rin is approximately Rib, which is 1 plus beta times the quantity Re plus Re. This can be written as Rpi times 1 plus Re over Re and is approximately Rpi times 1 plus GmRe. Therefore, adding Re increases Rin by about 1 plus GmRe. At the same time, the open circuit voltage gain becomes negative Rc over Re plus Re, which is the original gain divided by about 1 plus GmRe. This is the same conclusion we obtained in the previous small signal analysis chapter. So once again, adding the emitter resistor Re increases the input resistance by about 1 plus GmRe, but it also decreases the open circuit voltage gain by about 1 plus GmRe. The advantages and disadvantages are the same as those listed in the previous small signal BJT analysis section. This concludes the introduction to discrete BJT amplifier circuits, focusing on the common emitter amplifier. Please look forward to the next lecture. See you next time. Bye-bye.